In this video, we're going to talk about some of the basics of Markov chains. First of all, we want to talk about, more generally, the idea of a stochastic process, which is a sequence of random variables that's usually indexed by time. So now, that could be two possible types. We could have a discrete time stochastic process, where we have a sequence xn, so x0, x1, x2, etc., or continuous time, where we have xt, or sometimes x of t, where t is just a positive real number. And each of those xi's, or those xn's or xt's, can take on various values. The values that those random variables can take on is known as the state space of that stochastic process. And again, there are two types. Those xi's could be discrete random variables or continuous random variables. Notation-wise, if xn equals I, we say that the process is in state I at time or step n. So because there's discrete and continuous for both the stochastic processes time and state space, there's altogether four types of stochastic processes. We could think about the state space being discrete or continuous and the time being discrete or continuous. And I want you to take a second and see if you can think of some examples of each of these four possible types of processes. For the fully discrete case, we could have wins or losses of games or of a sports team. So each game would be discrete, and on each game, we could either have a win or a loss. So there's two possible outcomes. That's a discrete variable, and games themselves are discrete. There's game 1, game 2, game 3. So the time is discrete. If we want a discrete state space with a continuous time, we could think about the number of people in a population. So there's only integer numbers of people that exist, but someone could be born or die at any time. So the number in a population would be a continuous time, but discrete state space stochastic process. The opposite, where we have continuous state space but discrete time, could be something like the daily high price of a stock or the daily closing price of a stock. The price itself would be modeled by a continuous random variable, but there's only one observation per day, so it's going to be discrete time but continuous state space. Or finally, the fully continuous case, we could think about the temperature at time t. Temperature itself would be modeled as a continuous random variable, and that can change at any time. So the temperature at time t would be a continuous time with a continuous state space. Here's some more examples. We could have bond rating would be fully discrete. The number of cases of a disease would be discrete state space but continuous time. The maximum temperature on a given day would be continuous state space but discrete time. And the price of a stock at time t would be fully continuous. See if you can think of some more ideas for each of these. When we look at that first case there, discrete time and discrete state space, that's what we call discrete time Markov chains, or DTMCs. That's what we'll be looking at in chapter 4. Down here, with the discrete state space but continuous time, we have an example that could be a Poisson process, which we're going to be looking at in chapter 5. There are other processes that are not Poisson, but that's the one we're going to be looking at. And then finally, in the continuous case, an example of that would be Brownian motion, which we're going to be discussing in chapter 6. We're not actually talking about that fourth case. There's some neat stuff, but it doesn't really fit into the course. So this is kind of a preview here of the whole rest of the course, chapter 4, 5, and 6, looking at these different types of stochastic processes. All right, for now, let's move back into chapter 4, into the fully discrete world, where we have discrete state space and discrete time. I want to define something known as the Markov property. So we say a stochastic process has this Markov property if the following holds. If the probability that the process is in state j at time n+1, given the whole history of the process, so the process being in state I at time n, and in all of its other previous states at all of its other previous times, if this is equal to the conditional probability that the process is in state j at time n+1, given it's in state I at time n. And this would have to be true for all values of I, j, and n. Let's break this down a little bit. On the left here, we have the future of the process, so where the process is going to be one step from now. Here is what we could call the present. And then the rest of these values here is the past history of the process. So basically, that's saying that if we know the current state of the Markov chain, that tells us everything we need to know about the future. The future only depends on the present, not on the past history. We can ignore that if we know where we are at time n. That tells us everything about where we can go next at time n+1. Now we're ready to define a Markov chain. So formally, a discrete time Markov chain, which we could call a DTMC or just an MC for short, is going to have the following three conditions. First of all, it has to be a discrete time stochastic process. So that means it's indexed by time. There's values x0, x1, x2, x3, etc. Second, it has to have a discrete state space. So each of those xn's has to be a discrete random variable, so with a countable or finite range. And finally, not surprising based on the name, it has to have the Markov property. So those are the three conditions of any discrete time Markov chain. We have to have those: discrete time, discrete state space, and the Markov property. And again, like every model, it's always a good idea to think about whether the conditions for this model will hold in real life for the situation that you're trying to model. We'll be focusing on that a lot, seeing if these conditions actually make sense in real life. In addition, for this course, we're going to assume that the probabilities of moving from state to state do not change over time. So essentially, we're assuming that it's a time homogeneous stochastic process. And what that means is this probability here, the probability of moving from state I at time n to state j at time n plus 1, is not going to depend on n. So we can just call this Pij. Notice that this is going to depend on I and j, but not on n. We don't actually need to know when this step is occurring. So whether it's occurring from step 0 to step 1 or step 100 to step 101, all we need to know is where we're going from, state I, and where we're going to, state j. So if we have all of these Pij's, we can take them and arrange them into a matrix. So we can take these probabilities of moving from state to state and put them into a matrix which we call capital P. So it'll just be P11, P12, etc. up to P1K, and the bottom line there is PK1, PK2, etc. to PKK. Now this is going to be a square matrix, K by K, where K is the size or magnitude of the state space. So how many possible values X can take on. Now that could be finite or it could be infinite. So we might get an infinite matrix, but for now we'll start off with finite chains. But it is going to be square for sure, because we have to have all the places the chain can go from and all the places the chain can go to. This P matrix is known as the one-step transition probability matrix. That's quite a mouthful, so sometimes we call that a TPM, or actually sometimes I'll just call it a transition matrix. That's what we mean. So it contains, again, the probabilities of moving from each state to each state in a single step in this Markov chain. And the cool thing about it is that it uniquely defines the Markov chain. So if we know the transition probability matrix P, we know literally everything there is to know about the Markov chain. There's no other information that we need to find anything about it. It contains all of the information in one nice tiny package. There's some neat properties that this matrix is going to have. First of all of the elements are going to be non-negative. So Pij is greater than 0 for all I and j. And secondly, if we sum across the rows, that is going to sum up to 1. So if we take the sum as j goes from 1 up to k, the size of the state space of Pij, that will equal 1 for each of those rows. So again, informally, we say all the elements are non-negative and the rows will sum to 1. I want you to take a second and think about how you could prove those two properties or why they make logical sense. So think about that for a second before I tell you the answer. Number one is pretty obvious. They're all probabilities, and probabilities are non-negative, so boom, done. Axiom 1, I think. The second one's a little more interesting. This is sort of saying Pij is the probability of going from state I to state j. And we have to go somewhere, right? If we're in state I at step n, we have to be somewhere at step n plus 1. So if we add up over all of the possible places we can be at step n plus 1, that will give us 1. So it's kind of like, I guess, axiom 2 and the additivity axiom. If we add up all of the possible places we could be, we have to be somewhere, so that has to give us a probability of 1. Any square matrix that actually satisfies these two properties, so having all non-negative elements and the rows summing to 1, is known as a stochastic matrix. It's a special type of matrix. And the really cool thing is that any stochastic matrix you could possibly write down is the transition probability matrix for some Markov chain. I think that's really cool. You could literally take out a piece of paper, write down a matrix of any size that you like, a square matrix of any size that you like. As long as the elements are non-negative and the rows sum to 1, I could create a Markov chain with that transition probability matrix. And it completely uniquely defines it. So there's a one-to-one relationship between Markov chains and their corresponding stochastic matrices. All right, let's look at some examples. For example 1, we'll just consider the simplest kind, a simple two-state chain. So our state space S is just 1 and 2. And, that's pretty boring, so we could imagine those two states as representing two things that we care about. So that could be the rain or no rain, win or loss of a team, or even two states of the stock market could be in, a bull market or a bear market on a particular day. So we have two possible states that the chain can be in on any day or any step. So for our transition probability matrix, we know it's going to be a 2x2 matrix because there are two states in the chain. And the other thing we know is that the elements are non-negative and add up to 1. So let's see what this matrix has to look like. Imagine that first component there is alpha, and we know that alpha must be non-negative. And then we also know that the rows have to sum to 1, which means this term there is got to be 1 minus alpha, and that also means that alpha must be less than or equal to 1, because otherwise that element there would be negative. So that gives us our first row. Similarly, for the second row, if we let this element here be beta, then we know that beta must be greater than or equal to 0. And then finally, the last remaining element will be 1 minus beta, and that means beta needs to be less than or equal to 1. So that defines all of the possible ways that the transition probability matrix can look for a two-state chain. I want you to notice something here, that the columns don't necessarily sum to anything in particular. There's nothing that says that alpha and beta have to be equal to each other. So the rows must sum to 1, but the columns do not have to. And in here, what we're saying with this kind of chain is that the most recent result is allowed to affect the next possible result. So if we know the state today, if we know that it's raining today, that tells us everything we need to know about tomorrow. It doesn't matter that it's been raining for 3 days straight. That doesn't help or hurt getting rain tomorrow. So with the Markov property, we can ignore the history. We don't need to know anything that happened before today. If we know what happened today, that tells us what's going to happen tomorrow. We might have a situation, though, where we do want to have dependence from further back in time. So I'm going to imagine winning or losing again as an example, but imagine that whether a team wins or loses depends on the last 2 games that they've played in the following way. If they've won both of their last 2 games, then the probability they win the next game is 0.7. So they're kind of on a winning streak, they're feeling good. If they've won both of the last 2, they have a pretty high probability of winning. If they have lost both of the last 2 games, the probability they win their next game is only 0.2. So maybe they're feeling a little bit demoralized from losing twice in a row, so they have a lower probability of winning their next game. And otherwise, so if they've won one of the last 2 games, we say they have an even chance of winning. So these probabilities are completely made up. Just for this example, you could find some data on this maybe. That's a great idea for a project, actually, if someone wants to do that. So we have all of these probabilities based on the last 2 games that they've played. Now think about this. Could we actually model this as a Markov chain with 2 states? So letting state 1 be win and state 2 be loss. Think about that for a second. Can we do this? Spoiler alert. No, we can't. It's going to violate the Markov property because we're told right in the very beginning that whether they win or lose the last 2 games has an impact on winning the next game. So if all we know is their current, most recent game result, win or loss, that doesn't tell us enough about what's going to happen on the next game. If we know that they won their last game, we can't tell if their probability of winning the next one is going to be 0.7 or 0.5. And similarly, if they lost the most recent game, we can't tell if their probability of winning is going to be 0.2 or 0.5. Because it depends on the last 2 games. So if we really want to model this with a Markov chain, we need to expand the state space. Instead, we're going to define 4 states, 2 to the 2, as follows. We'll say that the process is in a particular state, 1, 2, 3, or 4, if the following holds. Thinking about the result on game n-1, it could be win or loss. And thinking about the result of game n could be win or loss as follows. So again, just to be clear, we say the process is in state 1 at time n if game n-1 and game n were both wins. we say the process is in state 2 at time n. If they won game n minus 1 and they lost the most recent game, etc. So now with these 4 states, let's see if we can define the transition probability matrix. We have the information now to be able to do that. So again, because we have 4 states, this transition probability matrix P is going to be 4 by 4. And let's see about filling in some of these values. Imagine we start in state 1. So that tells us that we've won the last 2 games, game n minus 1 and then game n, and we're thinking about what happens next. So what could happen on this next game? Well, there's 2 possibilities. Either we win it or we lose it. And at this point, we win with probability 0.7 and we lose with probability 0.3. That was from the value that we were given above. Because they're on a winning streak, they've won the most recent 2 games, they have a 0.7 chance of winning the next game and thus a 0.3 probability of losing. Well, if we win, then the most recent 2 games are win-win, which means that we're in state 1 at this point. Because win-win in a row is corresponding to state 1. But if we lose, then what state are we in? Well, looking at our chart, we're in state 2. So that tells us that from state 1, we go to state 1 with probability 0.7 or to state 2 with probability 0.3. So we can take those values and put them into the transition matrix here. 0.7 for P11 and 0.3 for P12. But the rows sum to 1, and they're all non-negative, so that means the last 2 elements in that row must be 0. Think about that for a second. It's not possible to go directly from state 1 to state 3 or 4 after a single additional game. Why is that? Well, if you tried to go from state 1 to state 4, let's say, going from a 2-game winning streak to a 2-game losing streak, it cannot happen in a single game. So that's why that term is 0. Let's try another row. So imagine we're starting from state 2, which means we won 2 games ago and we lost the most recent game. And now we're thinking about what happens next. So similarly, we could win or lose. And in this case, the probability is 0.5 for both of those cases, because this was one of those. We're not on a winning streak. We're not on a losing streak. We're just sort of normal. Okay, so what state are we in if we win? Loss-win corresponds to state 3. And if we lose, we're now on a 2-game losing streak. So we're in state 4. So again, we can put these probabilities into the matrix. From state 2 going to state 3 has a probability of 0.5, and same for going from 2 to 4. But going from 2 to 1 or 2 to 2 is not possible, so those values are 0. I'll fill in the rest of the values here, like this, and I want you to give this a try. Follow the exact same procedure that we did from state 1 and from state 2 for 3 and 4, and make sure that you can understand where the values in this matrix are coming from. So that is everything for this video. We've defined a Markov chain as a discrete time stochastic process with a discrete state space and the Markov property. So that's telling us that the future only depends on the present, not the past. That kind of sounds like an inspirational quote, actually. And then we have this idea of the transition probability matrix, where we have the probability of going from each state to each state, Pij, which we can arrange into a matrix. We'll see lots more examples in the next video. See you then.